Okay, we're doing UGM UCM practice problem number 4, looking at a long jumper who is on the surface of Mercury and assuming this person does not freeze or melt, depending on what side of Mercury they're on. So we're near the surface, so the force on the person is mg, but the g is not our normal Earth g, it's Mercury's g. So to find that, I'm going to use a ratio. You could look up those numbers and all, but ratio is easier here, as it pretty much always is. If it's usable, it's always easier. So g times the mass of Mercury over the radius of Mercury squared divided by g times the mass of Earth over the radius of Earth squared. Mass Mercury over mass Earth times radius of Earth over radius of Mercury squared. So those ratios are 5.5%, and that's 1 over 38% squared. So she can leap 6.5 meters on Earth. We're going to assume that's her max distance. That's sort of the implication, which tells me that theta is 45 degrees. So we'll keep the theta and the initial v the same on Mercury as it was on Earth. And instead of solving for anything, I'm going to use a ratio. This is, when you're doing long jump, you're over level ground, so this is a range equation territory. And I'll make a ratio of my range equations. Everything's actually the same except for the g's. Oops, g Earth there. So, but it's because the division is an inverse ratio. So the delta x that you would go on Mercury is the delta x that you would go on Earth times the ratio of those g's, and this is the ratio of those g's. Well, the inverse of it is what we want. And if we take that and multiply by 6.5 meters, which is a good long jump, by the way, 17.1 meters, that would be a terrific long jump. Now, if we look at what factor longer she would stay in the air, we need to figure out that time by doing some kinematics. The delta y is 0, there's a vi, there's a theta of 45 degrees. Actually, what I'm at the top, her v is like that. At the end, her v is like that. We'll go through the whole. You could do this by cutting the problem in half and then multiplying by 2, or not. It doesn't matter. I think I'm going to do it all the way to the end. So my delta y really is 0. Delta t is unknown. I'll call right a positive, and I'll call. So my a is negative. And I have a delta x like this. So let's see, if we look at delta y equals vi y delta t minus 1/2 g delta t squared, the delta y is 0, so I can divide through one of these delta t's and solve for delta t. It will be 2 VIY over g. So I'm going to go ahead and ratio that. The VI and the angle are the same for both, so I can cancel that. So it actually ends up with the same ratio. That's not always the case. We could have a square or something in there, but in this case we we end up not having that. So my factor is the same factor that it was up there, 0.38 squared over 0.055. It's 2.63 times as long in the air on one as the other, which you could also make a conceptual argument to solve this problem that if her VIX is the same and she went 2.63 times further on Mercury, then she must have stayed in the air 2.63 times as long.